Hello, this is Andy Schweitzer, and this is a se series of videos that are talking about solutions. Today we're talking about how do I make a solution. Now, in this case, how do I physically make a solution versus how do I actually make it on, on paper first, calculate all the properties of it. And that is what I'm going to calculate today is more of how do I make a solution. Now I'm talking just on paper. Okay. Now there are two ways in which you can make a solution. Now I'm talking about a solid dissolving into a some sort of solvent, and this will give me a solution. Now this thing could be a gas, and you could bubble a gas into a solution. That would be another way to get that thing to happen. But in this case, I'm looking at a solid, okay? And the other one would be to have some liquid, and you're simply going to add water, or your solvent, and that will also give you your solution. So I can dissolve a solid, or I can simply dilute. This is called a dilution. A liquid to get a new solution here, okay? So I'm going to look at the solid first. Now, mathematically, how do I quantify this? Okay, it is going to be in some amount of stuff per stuff is how I generally call this, stuff per stuff. This is referring to the solute. This is referring to the solvent, or it could be referring to the solution. It is essentially some sort of ratio. Okay, things that have lots of stuff per stuff would be we call concentrated. And things that have small amount of stuff per solvent or whatever would be often referred to as dilute. So it's a relative term. Okay. Now, how do I do this? Well, there's literally a dozen or so different ways you can just lock up this ratio. And I don't know that one is necessarily better than others. It just depends on maybe convenience or just maybe historically which one happened to take on first, got popular first. So in chemistry, one that might be the most popular would be what's called molarity. That's one we'll use almost exclusively. It's symbolized by a large M, and it is defined as a ratio of moles of solute per liters of solution. So that's the volume of both the stuff dissolved and the solvent. So that's both things in the end. Otherwise, how does this work? Okay, well, there's a variable here, and a variable here. Of course, if you have a solution, and the more stuff you put into this solution, the more concentrated it's going to get. If this solute happens to have a color, you'd see the color get darker and darker and darker as less and less light can get through it. So mathematically, it's quite simple. We're going to simply say, okay, well, if I want to make a solution, okay, let's say I want to make a 3 molar solution that is going to be 100 milliliters in volume. So I have 1, 2, 3 variables here. And I will say also that moles can be kicked back and forth to grams if you happen to know the molar mass. So these are linked, so they're pretty much the same. So in this case, I'm giving up the molarity, the ending concentration, and the volume. So in this case, let's plug in, and it might say, okay, the question at this point might be how much solute do I need? Okay, that might be in moles, or it might simply be in mass. Okay, so in this case, all I would do is I'd simply say, okay, well, plug in what you know and solve for what you don't know. There's 3 molares, my concentration, and I want to find out my volume. Well, the volume has to be in liters, so that's 0.1 liters, and solve for moles. Multiply over, and x equals 0.3 moles of my solute. Let's just say hypothetically my solute is NaCl. At that point, the molar mass of NaCl is 58 grams per mole. So at this point, that's how much 1 mole weighs. So a tenth of a mole would weigh 5.8 grams. I have 3 of those, so it's about a little more than 15. But dot line, get rid of moles, go to grams. This is my molar mass ratio. 1 mole weighs 58 grams. 0.3 times 58 for an exact answer. 117.4 grams. So if I took 17.4 grams of my NaCl and plopped it into 100 milliliters of water, stir it up, let it dissolve, assuming it all dissolves, we would have a 3 molar solution. All right? So with the mathematics of this, various problems will be thrown at you. That's a real common problem. But otherwise, we have 1, 2, 3, essentially 4 variables, including the molar mass. I'll give you all the variables. You find the one that's missing. Okay. Now, for this particular method, this is how you would actually make something. They would give you a certain volume requested, a concentration requested, a volume requested. You'd find a number of moles and then grams you would need, and you'd simply at that point just dissolve it in that volume. All right. How you physically do that, we'll look at that in the future for future videos and how to physically do it in lab. So check around for that. It should be available. All right. Next up here is the last option, which is, okay, I looked at this using the molarity equals moles per liter formula. What is it would be if we took a liquid and we add a solvent to it? This is called a dilution. Okay, so I'm going to add on a little thing here, and let's see, how do you go about doing a dilution? Okay, now it's important to understand this picture-wise how this is going to work. Let's say we have a little beaker here, and let's just say this beaker contains 50 milliliters of volume, okay, and it contains just a certain amount of stuff. I'm going 2, 3, 4, 5, 6, 7, 8, 9, and 10, okay, and I'm going to take this thing here and I'm going to dump it into a bigger beaker, all right, and I'm going to make this thing, I got it wider, same volume. Let's just say this is now 100 milliliters. So I'm going to double my volume. Now what I didn't double, I doubled my solvent. What I didn't double is any of my solute. So technically, even though I doubled my volume, the solute, okay, or the is equal. All right, they are equal on both sides. So I have to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, even though my drawings are not proportionally doubled, you will see that there's the same amount of x's, larger area. So we're getting less concentrated. Okay. Now mathematically, the way this works out is this: molarity equals moles per liter, and what we've done here is, okay, well, let's set up a mathematics to compare these two. This guy has a molarity equals moles per liter. But between these two equations, the mole is equal. All right. So let's solve these equations. Molarity times volume, liters, equals moles. And then this is moles equals molarity times volume. I'm going to go 1, 1, 2, 2. All right. So in this case, because the moles are equal, I can create a new formula between the two where I can drop out the moles. And in this case, the molarity of the first guy times the volume of the first guy equals the molarity, because this is going to cancel, those are equal, of the second guy times the volume of the second guy. And this is called the M1 V1 equals M2 V2. Now, you'll notice that this is a unique mathematical relationship. For a linear relationship, we have this x1 over y1 equals x2 over y2. Now, this is definitely not a linear relationship. I refer to this type of relationship as a reciprocal. And it's not as common as linear, but you'll definitely will see this. So we'll look at this and see how I came up with this reciprocal idea and how it works. But it is a definite, concrete type of relationship that we'll see happen in chemistry. Okay, so let's put the math in here and see what we got. My initial concentration for this guy is 10. Okay, I shouldn't say 10 per 50. So I'm going to just say that it was. I'll give it an arbitrary concentration because it's just a drawing. Let's go 5 molarity. Okay, and 50 milliliters. So my initial volume is 5 molarity. Initial concentration, initial volume is 50, and then my ending concentration, well, I don't know what that is, and my ending volume, though, I do know. My ending volume is 100, so I'll put 100 in here. Keep in mind that V2 equals V1 plus what you add to it. So 50 plus what I added. In this case, I have to double it. 5 times 5 is 25, so this is 250 equals x times 100. Divide the x out by 100, and the answer is x equals 2.5 molarity. Now, in this case, look at it conceptually wise, I doubled my volume times 2, so in this case, my concentration got cut in half. And this is your reciprocal relationship. As the molarity in a dilution, the molarity is always going to go down, and the volume will correspondingly then have to go up. If it goes down by 2, this is going to go up by, I should say, down by 1/2, then this is going to go up by 2. If your volume increases times 3, your concentration will drop by 1/3 to 1/3. But what it was. If this increases times 10, then my concentration will be 1/10 of what it used to be. This is a reciprocal relationship, and quite often you should be able to do some mathematics proportions in your head. Otherwise, this is the formula. You could use the original molarity formulas to do this problem as well. Put in your molarity, put in your volume, find your moles, plug your moles into the next problem, divide by the new volume, and then divide, and you get your new concentration. Same exact thing as what we have here. I again have 1, 2, 3, 4 variables. In this case, we solved for M2, but theoretically, realistically, any variable of these 4 that I give you, I'll give you 3 of them, you find the 4th one. So, how to make mathematically, how to quantify using moles per liter or molarity, and then otherwise we have making solutions with molarity or with a dilution. There are other types of concentrations, and I'll just take a moment here and types of concentrations. And there are some here. So, but they're all ideally the same. So we have percent by mass. This is one that we used in solids, but easily could be done. Would be the mass solute divided by total mass, okay, times 100. We could have percent by volume This is the one that actually is used more often in liquids because you can measure their volumes easily with a graduated cylinder. Would be the volume of solute divided by total volume times 100. Another one we might have for measuring this guy was called, it's not a percentage, would be a mole fraction. It is a little more common than these two, at least a volume for sure. Would be the moles of X divided by total moles. And this one's not times 100. So in this case, again, these are rate relationships. So this is saying that out of 100, if something is 50% by volume, well then it doesn't mean it actually has 50 out of 100. It's saying it could be 5 out of 10. So it's a relationship. This thing is basically saying, okay, out of 1, how many are there? Okay. So it's just a different relationship. It's based off 1 rather than 100. If you want to do out of 100, they have a thing called a mole percent. Not as common, would just be moles of X divided by total moles times 100 would give you a percentage of the particles due to that particular substance. Okay. Sometimes mole fractions used a little more in gases. Thank you very much.